And we are live. Nice. Didn't realize that. Superb. Will you wait for a couple of minutes before we start? Hi Devashish. Going good, man. Vipul, it won't be as good as yours. I saw yours yesterday. I was so happy to see you implement it in Rust. But yeah. And definitely I actually went through yours. Great. Okay, by the way, I'll be making a lot of mistakes, so bear with. But I've planned something, few very interesting optimizations that I very recently stumbled upon. So I'll try to cover most of them. Great, we'll get started. By the way, first of all, thank you so much for tuning in Friday evening. I know it's pretty odd time, but I had to do it sometime for some reason. I always wanted to live stream. Sure, I'll create my REPL. And by the way, I thought of setting up Go locally, VS Code. Few people were not happy with the font, so I'm like, hey, screw it. Let me use Replit for this. I just love this platform for some reason. No hassles, no setup thing. Do Go. I'll kick off Bloom filters. And public replit, go on. And I'll just link this in the description, so in case you'd want to copy paste or basically follow along, you can do that. REPL, saved, and I'll just copy paste my stream link as well. Always the stupid things. Cool. And where is stream link? And stream, no, not end stream. I'll copy this. We'll get started just a minute. One sec. I'll just retweet that I'm going live, just in case anyone else would want to tune in. Wait, going live. I am live. Let's get started. I'll choose Golang. I thought C, let's do C, but then I like no. Golang. It will be when I'll just basically while I'm doing this, I'll also talk about the thought process that I'm going through, so that in case and I'm sure it would help you all to understand how to approach things structurally. And I'll make mistakes. Bear with me. So I don't have superpowers that I can code seamlessly fine. Plus I cannot speak and talk. Speak and code at the same time. So yeah, I'll do my level best. I'll just see if my replit is properly set up. It is indeed. And fine. Okay. So yeah, first of all, I'm using replit as my ID so that I don't have a lot of hassles in setting up IDs and all. I could switch any language from one to another seamlessly. So one of the reasons why I love using Replit for most of my use, like for most of my prototypes like this. I've linked it in the description down below. You may want to hop along, see whatnot, you can do that. Okay, fine. So Bloom filters. Hope most of you are aware what Bloom filters are. In case not, just a quick refresher. It's a probabilistic data structure. Basically, whenever you hear the term filter, it is mostly a set of bits, or rather an array of bits, and what it does is it gives you false positives, but it definitely does not gives you false negative. It's a very theoretical way to say that it is possible, like when I add something to the bloom filter and I ask that, hey, does this item exist or not, bloom filter might say yes, even though the item is not there, right? So that's the false positive case that it throws at us, while the false negative case being if it is not there, then it would never say it is there. Oh, sorry, basically vice versa, right? So it would never have false negatives. So what does a bloom filter have? And by the way, Replit has this great ghostwriter that I will use. It's like hyper optimized for basically coding things, all things computer science. So I love that. So I'll just keep asking ghostwriter a bunch of questions, hoping it would answer those things correctly, and while I code. Okay, so bloom filter. Bloom filter, it's a array. Now here is the first like really interesting choice over here is bloom filter. It's an array of bytes. What we want to do is, I've seen, and for some reason I've seen a lot of implementations of bloom filter recently. Everyone seems to be using array of booleans. For example, what they would do is they would create a filter. They would create a filter which is array of booleans. Now, let's say if I want to create a boolean array, let me do that. I'll do make array of boolean. Let's say I want to have like 10,000 booleans, because at the end what we'll do is we'll take the value, we will pass it through the hash function, and we will set the corresponding bit to true or false over here in the bloom filter. So a lot of people just use array of boolean. Now the key thing is, although it works, but boolean is not one bit. At the end, when we say bloom filter, we take the value that we would want to put into the bloom filter, and when we say we are putting it into the bloom filter, we are setting that corresponding bit to 1 or 0. So when you are setting that corresponding bit to 1, if you use a boolean array, that boolean is definitely not 1 bit. Let's ask ghostwriter, how big is a bool in Golang? I'm not sure how big it is. If it's 1 bit, then that's fine. It's 1 byte. So it says that it's 1 byte. So if I use array, if I want to have a bloom filter of length 1000, which means I could have 1000 booleans, it would take me 1000 bytes to store it. We'll do hyper optimized version of this now. Okay, we'll not use array of boolean because because all we need is to store 1 and 0, right? So why waste 7 bits out of it? So let's do it this way. Let's go for a byte buffer. Let's go byte buffer of size. We'll start small. We'll start with 16, and we'll start with a small bloom filter. And what I would want to do is we'll take some test cases or other keys that we would want to put in. Keys, array of string. I'll say A, B, and C. In bloom filter, what we do is we take for key in range keys, I iterate over the key and add it to bloom filter. So bloom dot add and key k. I'll add key. Now let's define bloom. Bloom is struct bloom, or other capital bloom filter. Not type struct bloom filter, and I'll have bloom filter. I'll store filter as some element. I'll store filter as array of byte, and I'll have an init method. So func. It's suggestion. Scary, man. It actually very accurately suggested what we should write. New bloom filter size int star bloom filter. My God, AI will take over. Oh, I यार कोड यही कर देगा क्या? That's insane. Okay, fine. Okay, so when we define a bloom filter, we definitely need to tell how big the bloom filter should be. So what we'll do is we'll tell that, hey, I want to allocate bloom filter that would hold these many bytes. So I'll pass that as an argument as recommended, and it automatically did a make of it. but we'll write a little beautiful code over here. So okay, so this is how we will initialize the bloom filter. I did not write, Ghostwriter did, but fancy stuff. And I hope, and I'm sure basically GitHub Copilot does pretty similar things. But yeah, it understood I'm going to create a bloom filter and whatnot, and it just did it. Fine. So I want to have an add method on top of this as well. So bloom filter gave me a bloom filter object. I'll have an add method on it, and on bloom filter I'll have an add method which takes a string key, which takes a key of type string and does nothing with it. And in bloom filter I would want to do call add of it. So I'll change this function to add, and bloom is equal to new bloom filter. Let's say I create of size 60. So we'll go with limited seating there. Bloom filter, I've created a new bloom filter of size 16 and I'm calling add on it. Okay, now structurally it should, we have almost everything function, unuploaded, unused filter. Okay, I don't want to use it, fine. And I'll just quickly run and check if syntactically is all correct. Chalo, it's correct. Fine. Okay, now we have the basic structure in place, and now what I'll also do is I'll also, like, assume we have added something. I'll just iterate over the keys, and I'll also check if it exists or not. So exist and fmt println to say key and if it exists or not. So what I typically do is I have a habit of I first clear off all the inputs and outputs thing, and then I just solely focus on business logic. So that's what I'm doing. So I just created a small structural thing there, that hey, I have a structure where I'm storing some filter. I'll have an add function, and now I'll have an exists function that returns me a bool which says that hey, does this key exists in the bloom filter or not? Let's say return false. Okay, and then I will have this. I will do formatting. I want to import fmt is not imported yet, and I have done. Okay, fine. A false, B false, C false. Okay, fine. Now it's all business logic. Fine. Sure. Now when I'm trying to add something to the bloom filter, what I need to do is we take the key. Yeah, don't write code. Ghostwriter. Ghostwriter is writing code for me. Just, I want to write code. But it's pretty fascinating how much code AI can write for us. But more often than not, it just basically makes us quite a bit productive there. Fine. What next? What I was going to do? Adding to the bloom filter. Fine. So what we want to do is we take the key. We want to pass it through the hash function. Okay. We'll take the key, pass it through the hash function, and we'll get in some number. We'll have to mod it by size, and that corresponding bit needs to be set. Okay. Now interesting thing starts to creep up. Okay, fine. So let's start with the easy implementation, then we'll make it hyper optimized. So instead of doing size of or an array of bytes, let's do array of boolean, so that first we have a working bloom filter and then we'll optimize it. So let me just have array of boolean instead of array of byte, and what we'll do is we want to have a hash function. Let's ask Ghostwriter which is the best hash function for bloom filter. Which hash function should we use for bloom filter? And it spits out murmur hash. Fine, we'll use murmur hash. Okay, any Golang library for murmur hash. I'm not sure if it exists. I'm making so many. Oh, yeah, spitting out code again, man. Quite interesting. Fine. So murmur hash. Let's quickly check murmur. What's the key property of murmur hash? Non-cryptographic hash function suitable for general hash-based lookup created by someone. SM hasher. What's the property of it? Like, why not SHA? Like, that's my question. let's ask, why not SHA for Bloom filter? Cryptographic hash function, and so such big answer. You should consider SHA as the hash function if you have stricter security requirements. Okay. Oh, there seems to be an answer. They are also relatively slow to compute. Now. While cryptographic hash function like SHA have a good collision. Oh, sorry, you folks might not be able to see this. Yeah. Wait. I'll pull this out over here. Most of it would be there. I can move it up somehow. Okay, fine. I've just moved console down for a minute. Good enough. That's a big chaiga. Okay. While cryptographic hash functions like SHA have good collision resistance property, they are also relatively slow to compute compared to non-cryptographic hash function like murmur hash. Oh, it's about speed. So we can still use SHA, but SHA is slow. Fine. I didn't know that. Interesting. So murmur hash is most about speed. Just going through it. Seems complicated. Okay, that's fine. We don't need to know the details for now. We'll focus on implementation. There seems to be a library that gives us murmur hash. So I'll add it. And what I'll do is I'll create a utility func murmur. Instead of, okay, let's do this. I'll write a function murmur hash, which would murmur hash, which takes in a key and it takes in the size, the maximum bound within which it, because obviously murmur hash would be splitting in some huge range, like in 2 raised to 32 or 2 raised to 64 something. I'm not sure what the range is, but it would be a big enough range. So we would have to bring it within the bounds. So I'll just change it to the size that we are playing with, and it would spit out an integer in that range. So I'll just copy paste a bunch of code. Fine, I don't care how this works, but let's first get this running and then we'll figure it out. So hasher.write, copy and paste, result hasher.mean, copy and paste. Okay, I'll sort it out. What does each of this mean? So first we need to install this murmur hash library. So I'll go to here, go get installing, and okay, some seed is there. So what did they pass in seed? Oh, this UN32, they pass in something. Okay, so we'll define our own init. Oh, we can pass it in init function of Bloom filter itself. New Bloom filter. So new Bloom filter can initialize the hash function itself for us. We'll sort it out. Right. Okay, installation done. We have this. So we'll start with initializing the hasher, the murmur hash for us. So I'll move it over here, hasher, over here, where hasher. I'm not sure if I'm naming it correctly, but that's fine. So murmur hasher, and I'll set, what did I copy? Oh, this is the type. Got confused. What it is? Where hasher, and it was hash 32. That's what it is spitting out. And do it hash 32 to speed time dot now. I'll seed it with that. So when we, by the way, when we seed the hash function, like anytime you are you want to generate a hash function, by default you should pass some seed, because random number generators are not actual random number, they're pseudo random numbers, so they need seed to start with. So which is what we provided, a seed, and I'll import time as well. Fine. And hash 32, and this becomes our m hasher. Fine. We did m hasher and we initialized our m hasher to something, and m hasher dot write data, and okay, then we have result hasher dot sum32. Not sure what is this. It computed this. I think there has to be a way to clear it up as well. Reset. Fine. Okay. So what will we do? We will write key to this hasher and ask it to create a sum32, which returns us a result, and then we would reset the hash. So every time we are invoking it, we would be got it. Okay. So what we are doing with this murmur hash will take a key and a size, and it would spit out value in that range. So mod size, and now this is the result. So result colon equal to this hasher ki jagah m hasher, and we would return result. Okay, so the murmur hash function for us writes the key to the hasher, then generates the, and basically generates the 32-bit hash for us, mod size. We get it over here. We reset it so that we can reuse it for the next iteration. Otherwise, when you do write, it would be appending continuously, most probably. I cannot peek into this code, but that's what I guess it would do. Fine. Okay. And then we did reset and we returned result. Okay. So we have a hash function handy. We have this. Now we can write add. So in add, what we'll do, we'll pass the key through the murmur hash, and we will mod it by size. What's the size of the Bloom filter? We have it. We have function murmur hash. Let's move it to different. We'll move it to different file afterwards. Bloom filter this. Bloom filter this. Here we have size. We have passed it. Let's also keep it as a variable so that we can refer it. Right. So filter and size is equal to size, so that I can do here b dot size. Fine. So we took the num, we are passing the key string, and we would get the index. And what we'll do is b dot filter of idx is equal to true. Done. And while we do that, in exist, all we have to do is just b dot filter of idx. Now what's the idx? B dot filter of idx. Now we'll compute idx once again. Whatever key we have, it should run. What's the error? I don't think we did ghostwriter it for some time now, so I'll just move it up. Okay, and in fewer arguments, where not enough arguments, undefined function hash main.go line number 9. Okay. By the way, what was this hash? Ghostwriter, where did you get this hash from? Oh, import hash. Fine. I import hash. I don't have any problem. I'll run. And cannot use time.now, value of time.time. Oh, it needs to be integer. So dot unix and run. And run. Of type int64, you need int32. Oh, it gives int64. I convert it to int32. It's okay. We'll improve the correctness afterwards. That's fine. And cannot use int32. Let's type u int32. u int32. Our first aim should be to get things running, then we'll figure it out. Cannot use type key, type byte in argument of ham hash data. Oh, okay. It needs, instead of string, it needs byte. So we'll give byte to this. So, okay, we did this. Now what? Main.go, hasher.sum32 mod size, and hash 32 mod size. Invalid operation. What's invalid in that? U int 32 and size is int. So u int 32. We can safely typecast int to u int 32. Or rather, in this case, because it would always be positive, and result will be int 32, we'll convert it to int 32. I'm just being safe over here. I'm just trying to get this thing running first. Optimization will sort it out later. Okay. Line number 36. Here also copy paste will do that. So murmur hash of key, it's int 32 and this is int. So let's change size to int 32. That would solve most of the problems, because anyway, why would we have Bloom filter more than 4 billion entries? So that's fine. So int 32, we'll change it to int 32. I'm just simplifying this so that we don't have to change a lot of stuff there. So byte key updated. Oh, finally. Not enough argument to call. That's fine. My line number 36. Murmur hash. Oh, murmur hash we also passed in size. So we don't have to do this. We can just pass in size over here. Brilliant. Because in the murmur hash function we also pass size. That size over here. And it should be not size but b.size. Okay. It's still throwing some error. Hey, what did I do? Murmur hash takes in key and everywhere it needs to be in 32. Now it's gone. And the final nail in the coffin, instead of key, murmur hash takes in byte array. So we convert string to this and pass in b.size and done. What else? Now it should run man. Cannot use byte array of string value of byte as type string in murmur hash. Hey. Oh, murmur hash में string and we are passing byte. Fine. देखो ऐसे ही होता है. You tend to do something, you forget something else. चल जा. And we got something. We inserted A, we inserted B, we inserted C. We got A true, B true, C true. Okay. Our Bloom filter is of size 16. Now let me walk you through the code that we have written up until now. So, yeah, exactly, Arnav. We cannot go below 1 byte in Golang. That's why we would change this implementation to byte array to optimize the amount of data that we would have. So what did we do? We defined a hash function. Now did this. We defined a murmur hash. So we defined a function named murmur hash, which takes it a string and a size to define the bounds of it. Everything returns int 32 for us. We wrote it over here. We then took we ran the murmur hash on the key. We found out int 32 value. We modded by the size that we passed in. We got some index. This would be the actual index at which we would be setting it true or false. And in Bloom filter, we defined a filter, which is an array of bool, and a size int 32. We will optimize this to do. Let me add a to do. Optimize this. Okay. Then we defined a function Bloom filter. That size, initialize it with this one. Add basically takes keys, passes it to the hash function. Get gives me the index. I set that index corresponding to true. Then I check exist. In exist function we get the same index for the key. We check whatever the value is, true to true, false to false. By default everything is false. The corresponding values that we pass in are set to true. So we did A, B, C and it gave us true to true. But what would happen? I'm just trying to mimic a collision. A, B, it wrote everything for us. Brilliant. Okay. So from A to M, I have everything. Let me run. It gave me true for everything. Okay. So let's do this. I'll insert A, B and C. What we want to know is at which index did it write. So in the add function, let me print ln that wrote what's the key at index is idx. So this way we would know at which index are we writing. So out of 16 it wrote at 15, 5 and 11. So let me pass in A, B, C is done. Let me pass in D. And when I pass in D, what do I get? It wrote 12, 11, 11. Hey, here we see B and C has a collision, right? So B and C has a collision. Now if I'll just define a function bool, print bool, which would print the boolean Bloom filter entirely. So I'll just do fmt.println b.filter. Fine. Invoke कौन करेगा? fmt dot b dot print. Sorry, bloom dot print. Okay. Okay. Here we see all the values from 0th index, 1 index. We saw A going at 1, B going at 7, C going at 2, D going at 15. Oh, there is no. Oh, here we see pseudo random number generation in action. So what happened is last time we saw collision, this time we did not, because the hash function that was initialized, we passed in a seed value over here, and because in the seed value we pass in current time, so at every iteration, every time we are running the function, it is getting a new value as its seed. So random number will always generate with that seed. So for our testing purpose, it is better if we just hard code this to something. So u in 32, I'll hard code it to, let's say, 10. Right? So that we get very consistent, like we get basically deterministic values there. Arey bhai, हाँ भाई नहीं use किया time. Golang has such rigid rules. Okay. Oh yeah, we did not see collision. I'm just trying to get a collision there. It would become easier for us. Okay. We have this. So we have defined a Bloom filter of length 16. We wrote 4 keys to it, A, B, C and D. A was written at index 0. We see 0th index as true. B was written at index 5. We see index 5 as true. C was written at index 8, 5, 6, 7, 8. We see index 8 as true. We wrote D at 0. We see 0 as true. And we see A and D both go at 0. Right? So this is what it's probabilistic in nature. We take very less space to store this exact same information. Now we are checking for existence. Now let's try to find a case where we are looking for a key, because this is a sure shot thing where now if I say that fmt println, let's say if I want to check if E exists or not. So let me do bloom dot exist and I'll say E exists or not. Let's see, if we print if E exists or not. E got index at I need to I don't want to write that another function to see with what index would E go into. Okay, let's do this. Bloom.exist can return me for now as a hack. It can return me an integer and a boolean. It's just a hack so that I can see at which index it is checking. Just a hack, man. Just a hack. And ID exists. What it is, what type it is. In 32? Okay, in 32. Oh, we cannot print this, kya? Everyone has its own thing. So we'll print 3 things then. Key, index, and this. Go and go. It's just a thing up until the time we get it up and running. Okay, fine. So wrote A at 0, B at 5, C at 8, D at 0. We see this corresponding. E indexed at 1. We checked 1 is false. It is false. So it says E is present. No, it's E is not present. And indeed E is not present because we only wrote 4. Now let me check for F. And now when we check for F goes to 7. 7 is also not set. It is giving us false. Now we do G and we run it. G goes to 2. 2 is also false. Very good. Arey collision, Baba, collision. I'm looking for collision. H. Now we got a collision. Fine. So we wrote only 4 keys. Bloom.add, we only wrote 4 keys, A, B, C and D. We check for A, B, C, D over here through this loop and E, F, G, H. So here we clearly see the collision happening. where A stored at 0, like the corresponding index, like the corresponding bit is set to true, the boolean is set to true, then B at 5, C at 8 and D at 0, correct. Then when we checked, we could very clearly see that the bits 1, 7 and 2 were false. 1, 7 and 2 were false, and it indeed gave us false, which means the values are indeed not present. But when it gave us true, for H, we never wrote H to our Bloom filter, but H got indexed at 0 because of our murmur hash. 0 was true, so it said H is present, but in reality H is not present because we only wrote A, B, C and D. This is the false positive case. And this is where Bloom filter is an approximate data structure, right? So we see the collisions happening. We see Bloom filter having false positives where the value is not present, but it still says it is present. But it is indeed helping us do things in a very efficient way because we are not storing actual keys anywhere. All we are storing is just array of boolean in this implementation. We'll optimize it now. We are doing it at that time. So huge, like very less space. Imagine this 1 bit. Imagine this as 1 bit. We just have 16 elements that we are storing. So 16 bits of information, but we are able to hold A, B, C, D, 4 characters. In reality, if you would put this in a set, you would require pointers to construct a tree because assume that set is implemented with a tree. You can implement it with other ways, but the actual data needs to be stored. The pointers needs to be stored, very expensive. But here, what just happened is we stored the existence information of the Bloom filter in the filter, right? So that just makes it much easier for us, right? Or rather much efficient for us. Now we optimize this because we asked Ghostwriter that, hey, how big is a boolean in Golang? It said the boolean in data type in Golang is 1 byte. But if you look carefully, all we care is to set 1 bit of it. Why are we doing it the entire byte? Why are we wasting 7 bits? So let's optimize this. Let's play around with bits to optimize it, and then we would also see how it would how the number of hash functions would vary the false positivity rate, would plot graphs and all to understand how this varies. Okay, fine. It's a very nice exercise. I should do it more often. Okay, so first thing first, what we would change. So let's change the hash function. Reducing the size would increase the chances of collision. Arnav says reducing the size would increase the chances of collision. Yes, it would increase the chances of collision a lot. Reducing the size, multiples of 4s and 0 something to do with seed. Yeah, I have just hard-coded the seed, Shelly. I have just hard-coded the seed for now, just to induce the collision there. But now, let's have some fun. Now, first of all, what we'll do is we will mimic the entire load. So, randomized. We'll have huge size we would play with. So let's say we take a Bloom filter of size, let's say 1000, and we would now induce random seeds, random values. So let me take UUID. Do we have UUID? UUID.new. Wait, you generate UUID, or rather generate random strings in Golang. But how would we know if it exists or not? Hey, that's a huge function. But how big? How should we go about it? Just thinking it through. So what I'm trying to do is I'm trying to mimic the load of, because what I want to see is how false positivity rate increases as we keep adding values to it, right? So as we keep adding values to it, our false positivity rate should increase, because now for a lot of keys, we'll use the classic data science thing that we do. Okay, so let's do this. So the way we would test, or the way we would measure the false positivity rate of Bloom filter. So what we need to see is how for a limited size of bloom filter that we have, when we keep adding values to the bloom filter with fewer keys, it should be almost 0 false positivity rate. But as we keep adding lot of values in the bloom filter, because we have limited number of bits, almost all of them would be filled up, then the false positivity rate should go up, right? So let's just quickly do that thing. So what I'll do is I'll create a test data set. Let me create a data set, and data set would be a string data set because that's what we have been playing with. So I'll create a test data set of, let's say, 1000 random words. So let me take UUID as words. Generate UUID in Golang. So I'm just above. So what I care is I just want a simple UUID to work with. Like UUID would become my string here. Go get, and I'll do a copy paste. So what I'm doing is I'm preparing a data set for I equal to 0, I is less than 1000, I plus plus, and for I'll generate a UUID, UUID.new and u.string. So what I'm doing is I will store this in a map just so that we can see what exists and what does not, so that we can compare the false positivity rate. Because what we aim is that if I have a bloom filter of size 1000, how would my false positivity rate increase over time, right? We need to know the inflection point, because initially we expect that false positivity rate should be 0, but over time it should increase, right? Because we are keeping on ingesting the keys in the bloom filter, right? So map of string of bool, because this is just my data set. So data set is equal to this, and where it is. And what I would do is I would keep adding data set of this equal to true. Okay, so I just prepared my random data set over here, and now I would pick few keys from this data set, copy paste UUID here, done. Okay, so I have prepared my data set. Now what I want to do is I want to iterate through first 10. Hey, let me do it in list trap. Why this complication? चुपचाप list में डालेगा. I don't want to overcomplicate my solution. It's simple enough. Data set equal to data set dot append. But how will I check if it is present or not? String dot contains. Okay. Let me store it at 2 places then. It's becoming far too complex than I thought. Like, actually, it's not the bloom filter which is complex. The other itself is complex. Unnecessary complication. Okay. So let me have. Okay. Let me converge on one. So array of string. I'll keep data set is equal to append. So I did this. I stored it in a string. I'll do data set is equal to make of string comma this, and I'll pass in the size as 0. I'll keep on adding. So now I have my data set. What I'll also check to make it the lookup efficient in the data set, I'll set data set map, where I'll have make map of string bool. How does it of u dot string again equal to true. Fine. Cool. So now we have prepared our data set. Now what we want to do is, we want to see that for the bloom filter that we have created, now bloom filter we have created of size 1000. We have prepared our data set which contains 1000 keys, 1000 random keys. Now what we will do is for each one of them, I'll keep inserting. So what I would want to do is for every 10 keys that I insert, I would measure what's the false positivity rate that I have. So I'll split this data set into test, into train and test. So train implies basically what I'm putting into the Bloom filter, the existence case, while half of them would not exist. So how should I go about it? For fixed Bloom filter size, as the number of keys increase, fine. So for I equal to 0, okay, for I equal to 0, I is less than len of data set and I plus equal to 2. So what we'll do is for every time we would add one thing into the data set, we would want to add something into the Bloom filter. So bloom dot add, and I would add data set of I. So I'm adding element into data set of I, and then I would want to check if that key exists or not. Okay, let me converge. I want to plot this. I want to plot this such that now we rotate this. This is working anyway. I want to put the false positivity rate of this. How should I go about it? I'm just trying to figure out an easy way to do so. Hardware, there are far too many things. I don't want to overcomplicate it. A basic Bloom filter is anyway working. I'm just trying to, what I want to do is I want to plot the false positivity rate of it. What should I do? What should I do? What should I do? I have the data set. I'll split it into this. I'll check for the key that exists, check for the key that does not exist. Okay, let's just do that. Fine. So I'll insert half of the keys. I'll insert half of the keys and I'll check for all the keys. And what we should see is we should see the number of correct and number of incorrect. So bloom dot exist and data sets of I. Fine. Okay. Okay. So where count equal to. So these are count of positives. False positivity rate is what? The keys that the Bloom filter says exist, but in reality it does not exist, right? So which are those keys? So what I've done over here is we would want to know the keys that exist and the keys that does not exist. So what I'll do is count of instead of this variables के ऊपर नीचे होता है, ठीक है. So we have inserted data set, added 1000, removed it. So what I'll do is I'll just insert data set of exist. So I'll do it for 500 and I'll change it to, so what I'm doing is I'm just splitting my data set into two half over here itself. So these are the ones that exist, and then I'm generating again, and I'll generate half of them again, which I'll say not exist, and I'm just creating two. In my data set I have 1000, but I'm splitting it into two. So data set exists, data set not exist. Data set exists, data set not exist. It would just make our life much simpler. Okay, so I've split my data set into two half, 500 here, 500 there. And now what we'll do is we have uuid.new. We have inserted, why third time? What did I do that? We've inserted into Bloom filter. And now we would want to see the size of it. It's much more interesting than I thought. Pretty interesting. I never thought it would be this huge. I thought it would be much simpler for us to implement it, to test it. But it's pretty interesting now. I'm far into this problem. For how do we iterate a map in Go? I forgot. How do we do that? For hey, I seriously forgot how to iterate map in Go. Oh, range is there. For key comma something, we don't want that. Range and dataset exist, and I'll do bloom.add, and I'll pass in key. Okay, done. And now for key, so all the key that should exist, we have added it into the bloom filter. Now we would iterate over all of them. Now we will maintain count of what bloom filter says exist, what actually exists, count of, no, we'll just count this. So what do we want to count? We want to count for key, for underscore key in the range bloom dataset. So for all the keys that exist in the dataset, all of them, we would see that what bloom filter says about it. So we says what bloom filter says about this key, if it exists or not, and we would see if it exists on dataset exist of key. Okay. So now if it exists in the dataset and bloom filter says it exists, it is true positive, right? So true positive plus plus. If bloom filter says exist, okay, what we care? We care if bloom filter says exist and it actually exists, then we do true positive plus plus, right? And if bloom filter says exist and the key actually does not exist, right? If the bloom filter says exist, if the bloom filter says exist, but in reality the key does not exist because we have not added the dataset underscore not exist ka keys in this, then we do not true positive, we do false positive plus plus. Hey, we just need this because we know how many keys we are testing. We are testing these many. We just will print after this iteration. Done. So what we want is false positive. We will set false positive equal to 0. We will do false positive divided by len of data set. Whew. Let's see, what do we get? We got error. Line 79. If okay, not okay, exist keys, false positive plus plus. Syntax error, cannot use underscore okay equal to data set dot exist as value. Hey, isn't that the syntax? Map of string of pool. Hey, ये तो करते. How to check if key exists in a map? Not JavaScript, Baba. Hey, yaar. I thought it would give me in this context, in map in Golang. That's what I did. That is something else. No. Underscore okay colon equal to map of key false positive plus plus. What like syntax error, cannot use underscore okay colon equal to dataset not exist of key value, key as value. What am I missing? Insert 50% of keys with lesson. You have to add colon. Ah, yeah. Thanks, man. Thanks. Colon, okay. Oh God, it wrote so many things. I have to remove the logging thing. Where did I wrote that? Done. Array float division. I have to convert it to float 64, and I'll convert this into float 64. Float 64. 0.188 is the false positivity rate, which means 18%. Pretty high. Okay. So now what we want to do is we want to see how it increases over time. So as we keep on insert, so what we just saw is our false positivity rate is 18%. I'll just multiply it by 100 also. It would just make life simple. So every time we run, we see around 19% of false positivity rate over here, right? Pretty interesting. So we inserted half of the keys. We took 100. We inserted half of the keys over there. But now if I increase the fraction, my Bloom filter size is 1000. But let me add 1500 keys into it, right? Definitely my false positivity rate should go like out of the place. It should be 100%. If it is not, then something's wrong. Then there is very high collision rate. What happened? Why is false positivity rate not increasing? I have a Bloom filter of size 100. We did something funny. It's still showing 50. Okay, that's interesting. Reducing the size of the Bloom filter now. It's showing 60. क्या गलत किया पापा? False positive rate. Huh. Quite interesting. Debug करना पड़ता है. Lots of learning. I equal to 0, I is less than 2500. I'm inserting into data set, and I'm checking for non-existent. I'm inserting all of them in my Bloom filter, setting Bloom filter. I have Bloom filter of size 16. I've set it to 1. Still it is 60. Hey, कुछ तो गड़बड़ है. Let me print my Bloom filter. Bloom.print. क्या मचाया है? Let's see. It's still showing 60. Oh no. Oh, okay. We are checking Bloom filter. Bloom filter will always say okay. Oh, Bloom filter will always say exist, right? In this case. But what we are checking is if it is not existent. Oh, okay. Number of false positives. This is where the problem is. So because we are checking, let's check. Number of false positives is 500. All of them. And we are dividing it by length of data set. Hey, if false positivity is 500, hey, what is length of data? God, this is pretty interesting. क्या पढ़ा है अपन ने? See, length of data set is 3000. 500 divided by 16.6. 500 divided by 3000. क्या मचा है इसमें? When the test yes, the test needs test. Okay, what did we do wrong? False positive 0. We are doing false positive. Let me get rid of this 100. Not sure if it is doing anything funny. It's definitely not. It's still doing that. So 500 over here. Let me change it to 500. See, devil always. Now it gave 0.5, which makes sense. Oh, it's simply dividing it by that, which means in the first case, oh, now it gave 0.5. Now let me change bloom filter to size 1000. Now 1.75. Now we got it. Now we got it. Now it's working. But it was actually working fine as well. There was no harm in it. We are just messing, like we are just doing something funny over here. False positive plus plus. So key bloom filter says it exists and data set not exist, and it is actually not existing in our data set. Then it means that it is a false positive. And we are doing false positive plus plus. But false positive divided by what? I think our division is wrong, because we should not divide it by the entire data set. We should divide it by what? Because it would always give me, because no, but we are iterating on the data set, right? We are iterating on the train on 500 and then test on 1000. They are correct. Basically 500 divided by 3000 is 16%. That's true. And which is why we are getting constantly 16-17 range mein. Okay, which means this seems correct. So false positivity rate seems correct. So just to confirm a few things, if I increase, which means our bloom filter is getting really heavily filled. If I increase the size of the bloom filter, false positivity rate should decrease. Let's see. Now it's 0. Now it's there, right? Okay. Let's do this. Okay. Now that we have converged, bloom filter of size 1, 0.5, our division seems wrong, because it should, like, for half of the keys it says true. Oh, barabar. Now, half present, half not present, it would be 0.5. Okay. And now if I increase my bloom filter size to 2, it should have some effect. It's so small that it's all true. This is exactly what we should plot, right? We are just testing for 1000 keys fixed. We would change the length of the bloom filter and we would see how it varies. So what I'll do, let's just put this in a loop. For j is equal to, let's start with 10. J is less than 10,000. 10,000. Like, because initial values would always be 0.5. 10,000, j plus equal to 100. I'm just iterating it by 100 at a time and printing the false positivity rate. Good. Now let's see what we get. 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. Come on. It's all 0.5 throughout. Oh. Bloom filter size J, Baba. Bloom filter size J. Sorry, my bad. J, अरे भाई in 32 is kind 32 खत्म भी होगा आज. ले भाई in 32. 49922. Now we see it is decreasing. Yes. Okay, we see it started with 0.5 because everything got collided there, and then it sharply decreased. See. 0.5, 0.5, 0.4, 0.3, 0.32, 0.27, 256, 238, 19, 171. We see as the length of the bloom filter. So for the fixed number of keys, where we put half in exist and half not exist, we see the false positivity rate decreasing to almost 0.03. So it started from 0.5 to it ranged. So from 50%, it dropped to 3% for 1000 keys. And so for 1000 keys and 10,000 as my bloom filter length. If I change it to, let's say 20,000, we should see almost 0. I'm just trying to bring in that 0 because there are far fewer collisions that are happening. There is enough space. Now, 0.013, so it went to 1.3%, right? But it's pretty decent. But now here, one beautiful thing that we see is that even though we increase the length by 2, like we make 2x, like from 10,000 to 20,000, there is not much difference here. If we see carefully, there is not much difference in this value. So here we see, we still see big enough value. So what this tells us is that you don't really need to have a massive bloom filter, because after a certain point in time, you would not see huge enough improvement, because here it was 0.5 and then here it is 0.07, 0.05, 0.03. The thing is, you stuck with the value, like you stay in the value that suits you the best. You don't have to go a really high range. So the point is, how should you estimate the size of a bloom filter? So this is exactly what we do. So very recently I had to implement a bloom filter, or rather I used a bloom filter by Redis. And what I did is I just did this number crunching, where I knew my ingestion rate, I knew the quote unquote maximum number of values that I would fit in. Then I did something very similar of an analysis. There is a formula, you can find it on the Wikipedia page, that gives us how big a bloom filter should be depending on the false positivity rate that you want, right? So here we see that false positivity rate does not change much after a certain range. And it tells us that be happy, be content with what false positivity rate that you need, and you size it out according to that. Great. Chalo. We faced a lot of bugs, but we solved it. Quite interesting. We doubted our implementation. Our implementation was correct all around, like all across. But that's fine. That's the beauty of live coding. You get some, you lose some. You learn something new. Okay. But now, we still want to do one final thing. Like I want to do one final thing. So, ingestion rate covered, this covered. Optimization. That's just one optimization. By the way, thanks folks for staying, for bearing with me for this. But let's do that one optimization where we want to do bit manipulation, right? Or galti karenge, or seekhenge usme. So bit manipulation. Here we see that the size of the boolean is 1 byte. What we were setting is we are actually setting that 1 byte here or there, like true or false. What we should do is we should not be wasting the 7 bits of that 1 byte, because all we care is 0 or 1. So can we change this to byte, which is where we would have something really interesting. So now what we do, we broke the code, now we have to fix it. So we'll still keep the size of the bloom filter, but if you look carefully, our iteration, the way we are doing, 100 to 10,000, the iteration that we had, they are all divisible by 8. So basically what we would do is, when we are assigning the size of the bloom filter, we would do, what we are doing is, our bloom filter is an array of bytes. Each byte is 1 bit. Does Golang have an int 8? I'm not sure if it has int 8. Let me check if it has int 8. It has int 8. Better. You int 8? Arey hai, sab hai bhai Golang. Nice. Okay. So I set my bloom filter to uint8, which means it's integer of, it's an unsigned integer of length 8 bits, right? So what we'll do is, when we set a value, we get an index, right? Now we would go to that bit in this array of integers and set that bit to 1. So we are making it space efficient now, because we earlier, for us to store 100 booleans, we were using for us to store 1000 booleans, we were using 1000 bytes. But now instead of that, we would use 1000 divided by 8 bytes, which is equal to 125. So from 1000 to 125 bytes. So 8x reduction in size is what we are getting. Okay, so we did this, the code breaks, now we have to fix it. Now the few things that would change is when we write it, the murmur hash function that we wrote, it gives us an index. But now what we know is each element of my array is 8 bits within that, 8, 8, 8, 8, 8. So if the murmur hash gives me, let's say 3, I don't have to do Bloom filter of 3 because I have each element contains 8 bits, and out of that I would ideally want to update the third bit in my gigantic bit array. For us, that bit array is actually array of integers. So I need to find out the index in the array and then the bit within that array, right? So what's the index in that array? So if my murmur hash function gives me 3, third bit is in the 0th element and the third bit within that. So if it gives me 9, then it would be in the first element of it. If it gives me 17, it would be in the second, right? So it's multiplied by 8. So my actual array index, so array index would be whatever IDX gave me divided by 8. Hey, how do you know, man? Is it listening? Hey, it also gave me modded. Hey, man, AI. The more I use, code ही लिखते भाई. Oh God. Why am I even writing the code? It's generating the code for us. It's exactly what we should. It's exactly what we should be like. We wanted to do. Man, it's scary. Okay, fine. So AIDX is the index of the element that needs to be manipulated, and within that, which bit is BIDX. So bit index, A index is the index in the array, B index is the index of the bit within that 8 bits of that we have. So it will be mod 8. And now what we'll do is we would change in this element. I would want to set that corresponding bit to true. How do we set bit to true? Is I do an OR of it, or and I want to set that one bit to true. So yes, that's exactly what I want to do. And I'll set that element is equal to, so element is equal to element bitwise or 1 left shift by those many bits. So bit is 0, it would not be shifting by anything. 1, done, done, done. Okay, done. So this would set that corresponding bit to true. Okay, so setting is done. Now, what do I want to do? Hey, is it really done? Oh, it's done. Now, get is also similar. Now, get means we want to get that corresponding bit out of it. So, how do we get? It's AI. I didn't believe it until I used this much of Ghostwriter. Sab code khud hi kar lo yaar. Okay, fine. Serious mode. Okay, so first what we want, same computation, AIDX, BIDX. Now what we want to get from that element, which is b dot filter AIDX, and from that we want to get that bit. How do we get that bit? That bit is equal to an AND of that corresponding bit. हाँ लिख दे भाई, तू ही कोड लिख दे. हाँ bit, I ANDed with that bit, but I want to discard all other bits. So it should be all other bits 0 and this bit as 1. Will this work? I'm not sure. B of filter of A of IDX, that and one right, one left should be added. It would work, right? It would work. So that's it. Because now I would just want to convert it to Boolean. If it works, I'm not sure. Let's see. नहीं लिया, नहीं चला. So if it's greater than 0 or equal to, if it is greater than 0, it's true, otherwise false. Okay, let me just counter validate that. B dot filter of a of idx. So for that element, and I want to and all other bits 0, that corresponding bit to 1. So if it is 1, then it is 1. Everything else is 0 would mask it out. That corresponding bit value would propagate. If it's 0, it's 0. If it's 1, it's 1. It would work. Let's run. 0.5, 0.5 match. Okay, let's run the loop and see if it if our value still matches. We ran it till 10,000. Let's do it till 10,000. Yes. Bloom filter working. It ended at 0.03, which is what we saw the last time as well. We also optimized the space now. Great. Fun. AI scared us today, isn't it? Okay, it's that simple, right? So we just optimize the space by a factor of 8, which is great, but we had to do a lot of bit manipulations. Fine. So again, as you see, you get some, you lose some. You had a large space, you could directly access that index and set it to true or false. But here what you did is you did a bunch of bit manipulation to get it done. A bunch of more CPU required, but you get some, you lose some, right? If space is more important, you do this. If CPU is more important, you do that, right? But we did very fancy stuff with Bloom filter. So we see that same pattern, we optimized it over here. Now, should we do one more? There is one more thing. Effect of hash functions, right? So up until now, we just use one hash function, right? Can we use multiple hash functions? So what we'll do is we'll not do this entire thing once again. So what we would do is we would run the same experiment with multiple hash functions now. So we'll take this one value. Let's say we take this one value, which is 10,000. We know for 10,000, the false positive rate is 0.02. If I run it again, 0.02, Hey, where did we add some randomness there? I thought it should give us the same thing always. Oh, UUID. Strings are different. Sorry. Strings are different, right? Strings are not same. Strings are different. Okay. So we know the false positivity rate is around 0.02. So we'll use the same number. Sorry. To do this. But now what I want to change as a parameter is number of hash functions. So up until now we used one hash function. Now let's use 3 hash functions. So I'll use 3 hash functions. One with seed value 100, one with seed value, let's say some random number, some random thing. M hasher 1, M hasher 2, M hasher. Wow. People would stop calling me engineer if I do this. Let me put it all inside an array so that I can change the size of it. What I'll do is I'll initialize it with random values, because what we want to do is we want to compare the effect of hash functions, no? So I'll put hash fns like this, and I'll change this hash function m hasher changes to array of hashes, and I'll keep it hash factor equal to this, and okay. So what I'm doing is I'm creating an array of hash functions so that we can see the effect of, I'm just typing some random number to simulate. I'm in a really good mood today for some reason. Okay, we have how many hash functions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 10 hash functions now. Now what will we do is we want to see the effect of hash function on the Bloom filter. So we would use the same Bloom filter, the same data set that we went with, 1000, but we'll keep the size of the Bloom filter same, but I'll just change it to 10,000. But what we will iterate on is we'll iterate on hash function, right? So we'll see the number of hash functions that we would use and then we would see how it affects the false positivity rate of my Bloom filter, right? We'll start with 1 and we'll go till 10. So for I equal to 0, I is less than len of hash functions. Hey, what's the variable name? Hash fns or fit. Hey, hash sure hash fns. Okay, so what will we do? We'll change it to len of hash functions I plus plus. So we want to start with at least 1. So I equal to 1 and I is equal to this. Okay, done. We'll see what happens. In case it breaks, it breaks. So now few things that we would want to change is when we are adding, we should pass how many hash functions are we considering, right? Earlier we were just passing keys, but now because that's a variable for us, that's why we are doing it. So we'll pass how many hash functions we are passing. So let's say we are passing I number of hash functions, right? And what we'll do is we'll print false positivity rate for each one of them. So every time, okay, let me just sort it out. So every time we are creating a new Bloom filter, every time we are doing add, we are passing the number of hash functions we would want to use to store it inside the filter, computing the false positivity rate like always and all. Okay, so in add functions we would change that the number of hash functions that we would want to do it with, and here we would apply the for loop. Okay, for I equal to 0, I is less than number of hash functions I plus plus, and I would put all of this inside a for loop, and instead of just using murmur hash, I would use hash functions of I. Oh no, I have this murmur hash function. Okay, so okay, we can pass hash function index. Okay, hash fn idx. So instead of using m hasher, it uses hash fns of hash function index to write it inside this, and then it resets that. Okay, done. So we compute murmur hash for that index. We'll get a lot of errors now. Okay, so where else are murmur hash? Okay, here is our murmur hash. Add may exist. Where is add function? Add. Okay, so for each of this hash function, we'll pass in the same murmur hash key b dot size and I. Right? So which hash function should we use for each hash function? So what we are doing is, for the number of hash functions, we would start with 1, 2, 3, 4 and so on and so forth. For each of the hash function, we are computing for the same result set what's the false positivity rate, and we are iterating, we are getting that murmur hash, we are using that specific hash function, we are putting it inside the Bloom filter, like setting the corresponding bit and computing. Fine. Let me throw and see bunch of errors first. Main.go line number 14, we'll first sort it out. अभी इधर क्या था? भाई साहब दो डाल दिए इधर बस. Okay, what else broke? Main line 61. हाँ, exist बचा. Okay, so here we'll also do that exact same thing. Oh, here when we are checking now in Bloom filter, when we use multiple hash functions, we need to check that if all of them. Okay, in Bloom filter, I would say the key is present if the values of, if for all the hash functions that I'm using, if all of them says yes, then I would say that it exists. Otherwise I would say it does not, right? So that's the idea. So I would need to keep an eye on if all of them are true or not, right? If all of them are true, so if I'm using 3 hash functions, I would use, when I'm storing, I would take my key, pass it through the first hash function, get the index, set it corresponding bit. Second hash function, same key, another index. Same as third hash function, same key, third index, I'm setting it. Right? Now I'm checking, I would do the exact opposite with all the 3 hash functions. Would use all the 3 hash functions, check for each of the hash function the generated index, go to that index, see if it exists or not. For second, see if it exists or not. Third, if it exists or not. If all the 3 says exist, then I would say it exists. Otherwise, I would say it does not. Right? So I would have to check if all of them are true or not. So a naive implementation of it is, let me take exist as an array. I know it's not a good code, but that's fine. Where exist, what do we want? We want array of boolean, and I would do a make of it. Array of boolean, length will be equal to number of hash functions, because we would need those many to be there. And I would check these exist and exist equal to append exist, return value remains same. The idea being, if any one of them is false, then I'd say it's false now. Correct. If any one of the hash, if any one of the index given by any one of the hash function is false, I would say it's false. So I don't need this. I would by default say exist equal to false. No, exist equal to true. Exist equal to true. And if any of the hash function says if exist is false, which means any of the hash function says it's false, I can immediately return. I don't need to check for other hash functions anyway. I can immediately return that this is false. Otherwise, I don't need this. I would say it's true. Simple. I would say it's true. And for now, I don't need index because we don't need it. And exist may I also need to pass the number of hash functions. I'll pass it here. And b.size remains as is. Murmur hash, I need to pass in which hash function I'm talking about. I'm done. Is it? Okay, let's just quickly go through it. For all the hash functions that I have, I am checking what the index for that corresponding hash function is, checking the bit if it says it exists or not. If it says it does not, I short circuit and I immediately return false, because if any one of them is false, I would say key does not exist. But if all of them are true, I would say key exists. Okay, let's run. Error. बिना उसके तो चलेगा नहीं अपने को. Line number 99. Oh god. Okay. Exist. I need to pass the index I for all the hash functions. Do we have? Hey, Bloom exist or not? Hey, fine. Exist. Do we need to pass hash functions? We need to pass all. We need to pass the length of the hash functions. Right? Length of the hash functions. But length of the hash functions is I. So I. Correct. I pass correct. Okay. Let's run. Hey, it ran. Oh. Interesting. See, for one hash function, it spit out 0.026. What it spit out the last time? We are doing 10,000 keys. 10,000? Yeah, we are doing length of the Bloom filter 10,000. Number of keys as 1,000. For one hash function, it spit out 0.026 as false positivity rate. And as the number of hash functions increased, it went till 0. It's pretty interesting, because now what it is happening is that because you have diversified your hash functions, you are using all of them at the same time. Now it's very low probability that all of those keys, like all of those corresponding bits, are set for two different keys with that exact same sequence. Very difficult. Right? So that's why it went down. But now, what it means is that because I'm using multiple hash functions, when I'm putting it in a Bloom filter, I am filling out bits very quickly. Which means that if I increase the hash functions to even, let's say, let's make it 20. Let's go beyond that, right? If I increase it, then it should be getting worse. Hey, all this starts from this only. Okay. No repetition. There is some repetition. Okay. Okay. Let's see if it increases. It's still 0, 0, 0. Hey, but you see, it took far long to compute, because the number of hash functions increased. It took far long to compute. Because now it has to do so much of computation while it is inserting and not. And now we see it's still 0. After some time, you see some collisions happening over here for this use case, but it totally depends on the random that we have. Yeah, let me write a code for this. I don't know. Let's change the number of hash functions to for I equal to 0, I is less than what? I is less than 100, I plus plus. Okay. Wait, I need to copy some few things. So I'll just do this. Time dot now dot unix, right? I'm just setting it with this, and hash functions is equal to make of hash function hash 32 and of length 0 for I equal to 0, I is less than. I'm just defining the number of hash functions that I have. Let's say I go with 100, and I just keep adding to that. I'm just lazy enough to, and there are a few mosquitoes roaming around. Fine. You don't need this. I am definitely sure I missed time. Let's run. Hey, what happened? Len of hash functions in it. Len of hash functions equal to append this. ये कुछ रन ही नहीं हुआ क्या पागल लगा है Hey, what did we do wrong man? undo पहले चलाएंगे कोड, then we'll do random stuff. Is this running? It is running. Hash functions equal to append time dot now. I am adding 100 hash functions u in 32, and I am inserting it in time. Perfect. And setting it to initial seeds. Oh, it's a pretty niche mistake. I get it. Wait. This is very interesting. I make this mistake more often than I would want to admit. So here what happened is, here I defined a global variable hash fns. Here I am doing a colon equal to. So it creates a local variable with name hash fns. Now it would work. Now it worked. But it spit out the same thing every time. Now what happened? I don't want to debug it again now. What did we do wrong? So number of hash functions. When in main function, what we are doing? We are adding len of hash functions I plus plus. What is len of hash functions? Let's see. Hey, did I not add it to the? Yeah, I did append hash functions equal to hash functions not append. क्या मचाया फिर से? fmt dot println len of hash functions. Last 10 minutes, folks. Then we'll off 100. अरे 100 ही तो डाला है भाई. Oh, फिर से a silly mistake somewhere. We initialize it to 0. Seed issue. I'm not sure if it's seed issue. Time dot now because they yes, it is seed issue because u in 32 will convert it to Unix gives in seconds within 1 second. Oh God, pretty interesting issue. Oh, brilliant. So now what is happening is Unix gives in seconds, and this entire iteration is finishing within 1 second. So they're all getting the exact same value. Okay, let's change this to a random integer. Oh God, never expected to run into these issues, but I'm so happy. By the way, thanks. Who said that? Thanks 2KIQ. You have a 2KIQ. Int 64. No, int 32. You int 32 भी देता है. दे दे भाई. You int 32 दे दे. Good. I'll just remove this you int 32 over here. Now let's see if it works. Please, please, please. है तेरी तो. हाँ भाई नहीं कर रहा उस टाइम. Work, please. 0, 0, 0, 0. It increased. Yes, yes, yes. It increased again. Finally, we saw what we wanted to see. Okay. So see how beautiful this is. And we could see a short circuit evaluation in action as well. So we learned, we saw very interesting issue. By the way, thanks again 2KIQ for this. Yeah, you do live up to your name, man. Okay, so we see this starting with 0.25 false positivity rate. It decreased to 0 for very long time, and then when your hash function increased till, let's say 30 something, then my false positivity rate again increased. It again increased, and it kept on increasing. See, it's increasing and increasing and increasing. 15%, 20%, and 23% tak it went. If I would have added more hash functions, it would have definitely. Imagine if I have 1000 hash functions for 1000 keys in a 1000 Bloom filter, false positivity rate will be 0.5 with respect to our example, because 50-50 case, right? It would have very high false positivity because every time it would be setting all the bits to 0, right? But it did increase. So this shows us that having large number of hash functions is good, but having far too many hash functions will make your program go slow, number one. Plus, after some point of time, you would see elevated false positivity rate. And if you look carefully, see the execution pattern. It's slow, 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 and then now see, it would pick up speed. Why is it happening? Because the way we checked for existence is if the index in my Bloom filter is 0 or is for that index is false, which means it does not exist for that corresponding index, for that corresponding hash function, we are immediately exiting short circuit evaluation, right? Because of the short circuiting, it is not requiring to iterate through all the hash functions when it encounters one of them does not exist. And that's why we see very speedy completion when my hash functions are very large, because of the way we wrote our code over here. If we change this logic and we evaluate it for all, and then we see if all of them are true or not, then it would have taken equal amount of time, or rather the time would have increased as with the hash function, but because of our short circuit evaluation, it did not. So this is interesting, but the most interesting thing, 2KIQ, thanks for that. I would have never guessed it. It would have taken me at least hours to debug what would have gone, what would have happened there. But that was fascinating issue that we saw with that seed, because time.now.unix, we just blindly use it as a random seed every time, but see how impactful that is. But again, on Bloom filters, we saw quite a few interesting things there, right? So very interesting things that we covered, very interesting issues that we tackled. We saw impact of hash functions, we saw impact of Bloom filter size. We measured the false positivity rate. We wrote a basic Bloom filter with Boolean array, and then we changed it to byte array, where we did bit manipulation to set that bit and all. We slashed the space usage by a factor of 8. Pretty interesting stuff. Right? Finally, Friday night done right. Thanks Thanks folks. Thanks folks for tuning in. I don't have anything more to do, but this was quite fun. By the way, you can hunt on my Replit and check this thing out. We did quite a few things there, so very interesting stuff. Thanks for tuning in, folks. This was fun. But do check out Replit in case you want. I have my join in link there in case you are interested. Hop along. I love not having hassle to set it up. But AI did scare the out of me for sure. Bit manipulation is writing. Hey, humans don't write good bit manipulation. AI understood we wanted to do mod 8 and like divide by 8 and mod 8. Matlab, had that. Fine. But at least helping us be productive there. Great, folks. Thanks so much. Thanks, folks, for tuning in. Very thanks again. Friday evening. Have some fun. I have a few meetings to catch up in the office, so I'll jump onto those meetings now. But quite interesting discussion with no-filter. Maybe next time I'll pick up something new. Now I'm thinking, because I had fun doing it. I'll definitely do it more often. Even though I make hundreds of mistakes, it's fine. At least basically getting our hands dirty, seeing these interesting issues makes us better engineers anyway. Great. Thanks folks for tuning in. I'll end the live stream now. I can go and implement it in C. Chalo, super. Thanks. Thank you so much, folks. Have a great evening. I'll stop the stream and stream. Yeah, Daksh, for sure. I loved it 100%. Because I could be me, right? That's the best part. I could be me rather than having that fully recorded stuff. I could be me. Chalo, thanks, folks.